Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalo and I'll be walking you through the chemistry course. In today's lesson, we're going to consider mass and volume relationship in reactions. Mass and volume relationships in reactions, and we'll look at the stoichiometry of reactants. We'll study the study of stoichiometry. Then we'll look at the volumetric analysis and also calculations involving volumetric analysis. So what do we mean by the word stoichiometry? When we hear stoichiometry, it simply talks about the measure or comparison of reactant flow and quantity of reactants and quantity of products produced. Quantity of reactants set into the reaction and quantity of products produced out of the reaction. So it's all about us measuring quantities. It's not a qualitative analysis, rather a quantitative analysis. We're measuring the quantities involved in the reaction, the numerical values involved in the reactions. Now, there's several levels at which this do exist. We have the first level, which is the consideration of mass. The first level, which is the consideration of mass. There is what we regard as the mole-mass relationship. The mole-mass relationship. So when we write our chemical expression or chemical equation, peradventure we're working with, let's take neutralization for as an example. We have sodium hydroxide plus HCl, that's hydrochloric acid, to produce sodium chloride and H2O, which is water. Of course, this is an aqueous solution. This is aqueous. This is aqueous, and this is liquid. So, what do we take note of? Of course, if you look at the particular chemical expression, it is a balanced chemical equation, and if we note everything as 1, 1, 1, 1 in front of it, so we can easily conclude that 1 mole of each of the substances is required. Each of the reactants requires 1 mole each, and the products are also 1 mole each. So we're talking about a mole. When we talk about mole now in this particular expression, how do we relate mole to the mass? How do we relate mole to the mass? The mole of a substance can be calculated as the mass. You can calculate the mole as the mass of the substance in the reaction divided by the molar mass of the substance. The mass of the substance involved in the reaction divided by the molar mass of the substance. So, peradventure, we're told that about say 11.5 sodium, peradventure we have been told about 20 sodium hydroxide is being reacted, 20 grams sodium hydroxide. Of course, we can go ahead to calculate how much mole it is of the sodium hydroxide is being injected into the system. We can calculate the molar mass of sodium hydroxide. We know that sodium is 23, oxygen is 16, and hydrogen is 1. When you sum this together, 23 plus 16 gives us 39. 39 plus 1 gives 40. So sodium hydroxide has a molar mass of 40, and we're talking about 20 grams of it. So that will be 20 grams if that is our mass. 20 grams. So that means we'll have 20 divided by 40. So the mole of the particular, if this particular quantity is being involved, is about 0.5 mole. 0.5 mole. So this is basically how we express mole in terms of mass. This is the establishing relationship between mole and mass. The mole of the substance equal to the mass of the substance divided by the molar mass of the substance. So let's take, for example, now we have known what amount of mole is actually here. So if we have to calculate peradventure how much of sodium chloride would be produced in terms of the mass of the sodium chloride that will be produced, then we can go ahead and calculate. To calculate the mass of the sodium chloride that will be produced, since one is here, one is here, one is here, one is here, that means one of these will produce one of these. One of each of this will produce one of both of this. So it automatically means we have 0.5 of this, which means we need just 0.5 of this, and 0.5 of this would be produced. So we can go ahead and calculate the molar mass of sodium chloride. Molar mass of sodium chloride, sodium is 23 and chlorine is 35.5. When you add them together, it will give us 58.5. So we also use the same formula. Mole equals to mass divided by molar mass. We know the molar mass. We're trying to calculate mass this time around. Hence, mass will be equal to mole times molar mass, which M will be equal to 0.5 multiplied by 58.5. So M will be equal to 29.25 grams. So this is the amount of sodium chloride that will be produced if 20 grams of sodium hydroxide is to be used in this particular reaction, and there is enough of sodium hydrochloric acid, or even excess of hydrochloric acid. Exactly 25.25 grams of sodium chloride would be produced. Let's also consider the volumetric aspect, that is when we're taking note of volumes. Well, also when we're taking note of volumes, there's a direct relationship between mole and volume. Yes, a direct relationship between the mole of a substance and volume of a substance. The beautiful thing is that the relationship between them is established as the mole of a substance equals to the volume of that substance divided by the volume at STP. The volume of that substance divided by the volume at STP. Now, the volume at STP is taken as 22.4 dm cube. 22.4 dm cube. So with the knowledge of this, we can go ahead to do our calculations regarding the mole of a substance. And of course, let's take this example of we have impartially combusted gas that is coming from the exhaust of a vehicle, and it is going into air. In that particular gas, we are having a total of 20 cm cube of carbon 2 oxide, and we're having air containing about 48 cm cube of oxygen. So we have to calculate what would be the residual gas, what will be the output gas. Of course, if we look at the relationship, we'll see that 2 molecules of carbon monoxide or carbon 2 oxide is required to react with 1 molecule of carbon oxygen to produce 2 molecules of carbon 4 oxide. So, in other words, what is needed? This is what is available. What is needed or what is required is, if we have 20 of this, we need only 10 of this to produce 20 of this. Now, of course, what will be required? Residual gas, that is remainder. Of course, this one will have no remainder. They will cross out. While this will give us a remainder of leftover of 38 cm cube of oxygen, and of course, the entire 20 cm cube of carbon dioxide would be available. This same principle of course, when we're having 2, 1, 2, also applies when you're working with mass, when you're working with other substances. So the output product would be 20 cm cube of carbon dioxide and 38 cm cube of oxygen. So the total volume that will be occupied by the exit gas would be the addition of these two, which would be about 58 cm cube. Of course, what is input is 68 cm cube, but what comes out of it is 58 cm cube. So this establishes the relationship between mole of a substance and the volume. Of course, this principle also, as I said earlier, applies also when you are working with solids. You can also experience such losses in quantity, that is quantitative loss. This loss, actually, you see it will balance out when you're calculating the mass. It will balance out when you're calculating the mass of the substance. So stoichiometry is used in calculating the volumes or the amount of substance, the mass, the volume that will be required for a particular reaction to be successful. Of course, on certain conditions, we want limited amount supply of certain materials. Certain conditions, we want excess of some certain materials. So with our knowledge of stoichiometry, we can do our ranging, we can do our evaluation to ensure that what we desire, what we want as our output product is our output product. All right. So far in this lesson, we've considered stoichiometry, and we've talked about stoichiometry of chemical reactions, and of course, we'll look at how stoichiometry is being applied. That is the study of stoichiometry. How is it being used? Of course, in a few seconds, some questions will be displayed on your screen. Please do answer them. We want to test your knowledge of what has been taught in this lesson so far. All right, let's discuss volumetric analysis. Volumetric analysis simply talks about considering volumes in chemical reactions, especially chemical reactions which involve liquids. So that's where we see volumetric analysis come into play. Chemical reactions such as titration reactions, you're mixing different chemicals together. We'll see volumetric analysis come into play. There are a couple of terminologies we should get familiar with so long as we are working with volumetric analysis. One of such terminologies is the concentration of a thing. The concentration of a thing. About now, you'll see the definition for concentration on your screen. Concentration of a thing is the amount of a substance of a thing, as is a solute in a particular solution. Is the amount of solute in a particular solution, and it is calculated in gram per dm cube, grams per dm cube, which is written this way, or in grams per dm cube. Also, we can also talk about the molarity of a substance. The molarity of a substance. The molarity of a substance, of course, being displayed on your screen about now as well, is the amount of a mole of a substance in a particular thing. So it is also calculated in mole per dm cube. It's calculated in mole per dm cube. And when we talk about a molar substance, it's a particular substance which solution contains 1 mole of a substance. It contains 1 mole of a substance in 1 dm cube of the solution. Let's take this question. We have the question: calculate the mass of anhydrous sodium trioxocarbonate 5 present in 300 cm cube of 1 molar of the substance. So we're having 1 molar. Let's pick out our parameters. First thing we know is the molarity. Molarity is 0.1 molar. Of course, we can always calculate the molar mass. We can see the expression. So the molar mass would be 2 multiplied by 23, because we're having 2 sodiums, plus 1 multiplied by 12 because we're having 1 carbon plus 3 multiplied by 16 because we're having 3 oxygens. So this is 46 plus 12 plus 48. This is 60, 100, and which is equal to 106 grams per mole. Okay, now to determine our molar mass, as the mole of the substance equal to, which is what we're asked to calculate. Okay, we're asked to calculate the mass. The mass will be equal to our mole multiplied by this. When you multiply, of course, the molarity should go away. So we'll have 106 grams per mole multiplied by 0.1 mole. And when we multiply, we'll get 10.6 grams. So this is the quantity, this is the amount in terms of grams of the substance present in the solution. So let's go to the B part, that's the A part. The B part says we should calculate the number of particles. The number of particles can be calculated using the Avogadro's number. We know that the mole equal to number of particles divided by Avogadro's number. So that will be number of particles, let me use N to represent that, will be equal to mole multiplied by AV numbers, which will give us 0.1 multiplied by AV number is 6.202, sorry, not 6.2, 6.02 times 10 raised to the power 23. So our number of particles will be 6.02 times 10 raised to the power 22. So that is the number of particles present in the substance. Alright, let's take this question. The question says, calculate the mass of anhydrous sodium trioxycarbonate 4 present in 300 cm cube of 0.1 molar of a substance. Also, we should calculate the number of the particles present in the solution. Well, for me, I'll say the first thing to take out is our formula, parameters. What are the parameters we have? We have the volume. Our volume is given as 300 cm cube. Let's remember we do work in dm cube and not cm cube. So we'll convert this to dm cube. That will be multiplied by, divided by 1000. That will give us 0.3 dm cube. All right. Now, next thing again to do, next parameter we can see is molarity. Molarity is 0.1 molar, and we know 1 molar is the same thing as 0.1 mole per dm cube. So next thing we can do is to calculate the molecular mass of the substance. So the molecular mass, capital M, equals, if we look at the structure, we have 2 sodium, so we have 2 multiplied by 23. We have 1 calcium, carbon, so we have 1 multiplied by 12. And we have 3 oxygen, so we have 3 multiplied by 16. When you solve this, this will give us 46 plus 12 plus 48, which equals to, this is 60, 106 gram per mole. 106 grams per mole. So we have to convert this molarity from molarity to concentration. So if we are calculating our concentration, our concentration will be equal to our molarity multiplied by our molecular mass. That's molarity multiplied by molar mass, which will give us 0.1 multiplied by 106, which will give us 10.6. Of course, this will change, the mole will cancel out, so we'll have what? Gram per dm cube. Grams per dm cube. So we have to calculate how much of the substance is inside 0.3 dm cube. So to calculate the amount of the substance, we'll simply multiply our concentration by dm cube to get the mass. Of course, we know that concentration multiplied by the volume will give us the mass. So our mass will be equal to concentration multiplied by volume, which will be multiplied by 0.3, and this will give us 3.18 grams. So we will have a total of 3.18 grams of the substance in this particular compound. So, and this is our A part. This is our A part. In the B part, we are asked to calculate the number of particles in it. We'll calculate our number of particles using the formula the mole equals to number of particles divided by the Avogadro's number. So let me take my number of particles as n, which is number of particles. It will be equal to the mole or concentration now. Concentration multiplied by Avogadro's number. Of course, what I really need is not just the concentration. I need the concentration with the volume, that is the mass. I need a mass that with the volume. So the mole, actually, that's what I'm supposed to use, mole, yes. Multiplied by the Avogadro's number. Because I have to consider the volume. I have to put the volume into consideration. So this will give me, when I multiply it, that will give me, I want to bring in the entire setup. That's my molarity and my volume. I want to bring them into the whole thing. Of course, if I should go ahead to do that, it means I'm going to simply ignore the part of it that talks about the molar mass. I'm going to ignore the part of it that talks about the molar mass, because the molar mass has actually no effect on it here. So I can go ahead and pick my volume and my molarity. So picking my volume and molarity, 0.1 multiplied by what's my volume, 0.3, then multiply all of that by 6.02 times 10 raised to the power 23. Multiplying this 1 and 2, let's take that away from that. Okay, to return 1, and I'll have 1.806 times 10 raised to the power 22 particles. So this is the number of particles that will be present in the substance. So that's how we go about the calculations involving volumetric analysis. All we just need to bear in mind is the formulas to work with. The ultimate formula to work with is MAVA over MBVB equals to the molarity of, or the concentration of the A, that is number of A. Let me just put it as A over that of B. So let's say we're working with sodium hydroxide plus H2SO4. Of course, we need 2 sodium hydroxide to balance the equation. This will give us sodium tetraososulfate 6 plus 2 molecules of water. Is it 2? No, not 2 molecules. Yes, 2 molecules of water. So, from this particular expression, we can see that we have if this is to be our B and this is to be our A, if this is to be our A and this is to be our B, and we have considered the molarity of A, considering the volume of A, consider the molarity of B, considering the volume of B, then our A here will be 2 and our B here would be 1, because according to the expression, according to the equation that we have from the board, from the chemical equation, 2 quantities or 2 mole of the base is required to react with 1 mole of the acid. So that's how we'll take our calculation. That's how we'll go about the calculation involving volumetric analysis. We've done a particular calculation before now. Alright, in this particular lesson, alright, before we go, also it's important to note that this particular method, this particular calculation can be used to calculate the water of crystallization of a substance, can be used to calculate the amount of mass of a reactant needed for a particular reaction to occur. It can be used to calculate the amount of resources that is being wasted or on unreacted substances in the setup. It can also be used to calculate the volume of products that will be produced. So, in this particular lesson, we studied mass and volume relationship in reactions. We discussed stoichiometry of reactions. Then we also looked at the study of stoichiometry, how it is being used, or what they use stoichiometry to do. Then we also looked at volumetric analysis, and we also did a calculation on volumetric analysis. In a few seconds, some questions will be displayed on your screen. Please do well by attempting them. And if there's any part of this video which any part of the question, any of the questions that prove to be difficult, you can look at the video one more time for clarification. Thank you.